So I don't know that there is a perfect way to put the subjects in our book in order. Our book has taken all the chapters on gas pollution, and it's actually put them into two separate parts. One is, hey, some pollution causes climate effects and others doesn't. But as we're reading through, specifically in this chapter about smog, I found it's now talking about acid rain, and then it's talking about particulates, and then in a later chapter it talks about particulates again, where I think for me it would be better if we just combined all of those things together. So I'm going to take some of the material that is in 3 and some of the material that's in 4 and just mesh them together. We are done with the smog aspect, mostly, but there is a little bit extra. There is a little bit extra because not all particles are the same. So PM is particulate matter. And actually this comes up in an interesting way in the next topic, which is acid rain, because in a really curious way, the world was better off when our emissions were sooty than we are now that they are clean. Mm-hmm. Nobody wants to go back, but you could argue if it was your job to be on debate team, or if it was your job to be a lawyer, you could argue, well, you're in this position because there's not the amount of soot that there used to be. And then we'll see this later. So particulate matter. So this gets to be things like soot and dust. No, that's all in the smoke. All right, well, if you've ever lit a fire, you know that there is smoke that goes with the flame, and then there is soot that rises but then comes back down because it has a mass, it has a particulate size that prevents it from riding the thermals. So there's a thing that they call PM10, and these are the particles that are smaller than 10 microns. If you are this small, I'm not sure how to spell inhalable. Does it have an E?
Oh gosh. Oh,
No, I don't think
correct.
it does. Then this is inhalable soot. And this is, you don't have to watch much late night television to see the ads for mesothelioma lawyers. Daytime television. Because sick people are at home. Lawyers buy time on broadcast televisions because sick people are at home. So all of your crash injury lawyers and your mesothelioma is a lung condition because you've breathed in particulate matter, and it's not going away. We thought it should be gone by now. There are very few coal miners left. There's very little asbestos left, and yet we're still suing the asbestos industry. We're still suing, not allowed to sue the tobacco industry anymore. The one great big settlement in the 1990s, that was it. That was it. It was billions and billions of dollars, one-time fine. And you can't sue them now. It's out in the open. Smoking is bad for you, officially. And if you do it, it's your fault. Yeah.
Nice.
So it kind of cleared the air for a while. And the tobacco companies are doing okay. Not great, because people don't smoke very much anymore.
Mm-mm.
We've made them be difficult. But yeah, inhalable smoke, you could see the smoke, but the ash is only on the outside paper part and tobacco part. What about all the inhalable stuff? So this is considered to be dangerous. This is the stuff that we want to monitor. Well, anything, everything is in balance. All of your body's systems are in balance, and if you were to impair one of those systems, it would have a knock-on effect in your other systems. So if you breathe in enough dust to limit your ability to absorb oxygen, now your body is straining to find that oxygen, and it does that by upping your blood pressure. And your pipes, your veins and your arteries have a capacity, a working capacity, which is, hey, this is a useful blood pressure. And when you exceed that blood pressure, valves fail, walls fail, membranes fail, and then you have a small to medium to large blood vessel event inside your brain, and and suffer the consequences for it. There is definitely a knock-on effect. One of the big effects, we mentioned black lung a couple of days ago, I don't know exactly when, but so mouth, again, never had biology, so I can't teach you all the parts, but the bronchi and bronchiola, and then into your lungs, right at the very end, so it goes down into little capillaries, and at the end of the capillaries, little air sacs called alveoli. And let's zoom in on one. Okay, so it's a little air sac that blows up, and there is a sensitive blood barrier right here that will allow oxygen and carbon dioxide to exchange. Okay, imagine for a second that you inhale a particle. If you're lucky, it's organic in terms of it's like a part of a leaf or something, because then it could perhaps rot, it could be broken down, it could turn into something else. Get rid of it, because we might possibly have a metabolism for it. Okay, worst case scenario, it's silica, it's sand, or it's that type of coal that we talked about a couple of days ago, the anthracite type, that has jagged edges and is pure carbon, and it's inorganic, it's not part of the living world. So this isn't any longer just a dot. It's a spiky dot. And every time you breathe in and breathe out, it scours around on the inside, like the P inside a whistle. Okay, this is damaging. This is chronically damaging. The why, smoking doesn't cause cancer. You can smoke a cigarette and not get cancer. You can smoke a cigarette for hundreds, thousands of cigarettes and not get cancer. But you're upping your chances because, you've got volatile organics that are carcinogens inside smoke, but you also have this. If you're a miner, coal, you have pneumocomiosis. If you're a quarry worker, you have silicosis. If you worked in the brake pad industry, you have asbestosis, because asbestos is a fiber. You get a fiber in there, and that every time you breathe in and out, that fiber just rattles around and jiggles around, and you can't get rid of it. So they become chronic injuries.
There's some really cool history on silicosis that I read up on a while back. It was from the early 20th century, and it was a bunch of the people at the quarry and the mine in the mountainside in Virginia, I believe. It was made up of the rock was silicon, I believe. It was like there was parts of it was silicon based or whatever, and it was basically massive cases of silicosis, and it was just like wiped out everyone.
Virginia, West Virginia.
West Virginia.
Yeah. That's central place for all kinds of health issues like this. We can make that be an essay.
I really liked it. It's really interesting.
So anything that you can do that mitigates this is a plus. All right, how do we get the soot out of the air?
Rain?
Yeah, there's a couple of really simple ways. If it rains, all the soot comes down. So why don't we just pretend it's raining? If we had sprinkler systems if I had somewhere that I knew was a source of particulate matter. When was the last time we saw a building be demolished? When was the last time you saw a road be built? We live in Austin. There's a stupid question. It's like this morning. Yeah. Okay. What goes alongside the people digging in the concrete and digging up the soil and doing everything else?
There's a lot of dust.
The trucks that drive up and down the road sprinkling them.
Oh.
You seen the sprinkler trucks? Yeah. Okay.
I'll take a video.
Yeah.
I want to report them.
Every time, every time you're gonna demolish a building,
Yep.
the building comes down, and then debris and soot, particulate matter goes up into the air. So they spray into the air water, and it catches the big particles. Gravity acts on, and they come down. It's the finer particles that we have to worry about. Yeah, so there's a couple of simple ways. If you can spray water, that's a big one. This is what you do in your own home. Do you have an air purifier? The pollen, which is small little particulate matter, pollen is particulate matter. And we know that we don't need a lot of that in the air. We only need micrograms of that in order to feel it, because there's an allergic response to it. But if you have an air purifier at home, a good chance is that it has an electrostatic plate in it, because the particles get charged just by being, and if you can fan them across a plate that has an electrical charge, they'll stick to that charge, they'll stick to that plate. And then all you have to do every now and then is wipe off that plate. Or the old-fashioned way is actually filter them through. What do we measure? Now this is out, if it's in the book, we haven't got to it yet. I haven't read the part about filtration yet.
Mm-hmm.
Do you have a filter in your house, in your apartment? Certain that you do. What do we measure filtration in?
I'm trying to remember what it said on my thing. I actually need to switch it out
Yeah.
too.
So
I always get the highest rating, I don't know.
I'm doing this from memory.
Right.
This might not be the American way of describing this, but we talk about what the mesh is and how fine the mesh is. So when you buy a filter, you'll get cubic feet per minute. Is probably what's stamped on the side of it, because we live in a non.
Feet per minute, yes. It's this one says 295 FPM.
Okay. Feet per minute. That means cubic feet per minute.
Mm-hmm.
I assume.
It is
And
CFM.
the wider open your holes are, you get more flow, because there's less resistance to flow. And they will let everything except the big particles through. If you make it the holes really, really small, the mesh really small, then that traps everything, but it doesn't allow for airflow. So they get clogged really quickly. Plus you don't have the airflow, and what is it that you want the airflow in your house to do? You want it to cool you down when you're hot and heat you up when you're cold, and if the air isn't flowing, people don't like it. So there's a happy medium in there for some people. That's why there's more than one type available. Also, if you have a really tight mesh on your filter, it's the same analogy as blood pressure. Gases are pressurizable. Liquids aren't, really not. So now your furnace is trying to push, your AC system is trying to push, and it can't get through. And so now it's backing up.
Mm-hmm.
It's building a back pressure on one side of the filter, which might not be great for your mechanical system.
Yeah.
So read whatever the manufacturer says. Okay, that's the last bit I want to say about that. Let's move on to the next topic. And everything is connected, because a couple of the culprit molecules in this next chapter, we've already seen. They were in the previous chapter. Let's talk about acid rain.
Yes.
Okay. What's an acid?
It is which document? What's it, H plus?
Yeah.
Into
So
solution.
if you give me the simplest one, it's probably a good place to start,
Right.
because in fact, for this entire chapter, I think it's the only one that we want to see.
Yeah, okay.
Under the Arrhenius definition, an acid increases the concentration of the H plus ion. The H plus ion is called hydronium, because hydrogen is an atom that contains one proton, one neutron, and one electron and no neutrons. And we're going to ionize this by losing an electron so that it becomes H plus. The hydronium ion is just a proton. It's a dissolved proton. And if you have dissolved protons in solution, you are now acidic. So anything that increases the H plus ion concentration is defined as being an acid. Okay. Now, that's a concentration. Good things about concentration is they're quantifiable. We can put numbers to those. Bad things about concentration is that the concentration of your acid could be 1 part per trillion, versus it could be double digits in molarity. We did a lab this morning where the acid was 12 molar straight out of the concentrated bottle. But I could dilute that down 1,000,000 times, 1,000,000,000,000 times. So I have a giant range in values of what concentration is. So instead of talking about concentration and using either mostly really, really small numbers that the general public doesn't understand, we have an acidity scale. It's pH. So the H plus concentration, we're going to give notation this. This is our notation. Anything that's in square brackets means concentration. So the thing inside the square brackets, H plus, is the acid. Square brackets of H plus means concentration of acid. pH is the negative log to the base 10 of the H plus concentration. Do we understand how log scales work?
Yes.
Not really.
Yeah.
Let's do it on the board for those watching at home. I'm going to give you a value, and I'm going to then have you find the log value of that value. Did this in Chemistry 1 yesterday. All right, I'm going to have numbers up here and numbers down here, but I'm going to start in the middle. When my value is 1, what is the log of 1?
Do you want to do it? I got it pulled up, so I don't want to just like try to zero. Here, use mine.
Oh,
Pretend
remember
like I
you
did.
had a calculator last year that was the worst calculator I've ever seen? You had to press and hold button. It was just insane. What the key presses you had to do to do the simplest function. Get yourself a 795 calculator from HEB or from Walmart. I like the Casios. Sharps are okay. TIs are too complicated. What's the log of 10?
Oh, it's just like log. I think it's just 1, right? Yeah, 1.
What's the log of 100?
Should be 2. 2.
What's the log of 1,000?
3.
What's the trend?
The number is 0.
Yeah.
Going up by.
The log represents the number of zeros in what we call the underlying value. This is the value, this is its function, this is its log. Okay? So, without looking at the calculator, what is the log of 1,000,000?
6.
Okay. Our concentrations of acids are likely to be small numbers. And certainly in the environmental realm, we're going to be looking at very small numbers, trace concentration numbers. What is the log of 0.1?
Yeah, number 3. I have to use that thing all the time.
-1.
What is the log of 0.01? And 0.001? Yeah. Okay. If your value is less than 1, your logs are now negative. it's really important. Lots of Americans don't do this, and it's not your fault, it's the way you were taught in middle school and high school of saying this value is 0.1. Nope, it's 0.1, and you need that 0 for later on. Okay, so the pH is the log of this value, and values of pH run from 0 to 14. This being most acidic. This being most basic. And this being neither basic nor acidic, this being neutral. And the fact that it runs from 0 to 14 tells us something additional. This is not a man-made scale. Humans would never invent a scale. Even Americans would not run a scale that ran between 0 and 14. It makes no sense at all.
We might measure things and, like, using.
You
football
know,
fields,
what is it? A pound, stone. There are 14 pounds in a stone.
Mhm.
Is that right? So 20.
pounds in a stone.
Yeah. Yeah. So it has been done. It's a stupid non-metric. Yeah, there are 16 ounces in a pound, and then there are 14 pounds in a stone.
Yep.
So people of a certain age from England, if you ask them how heavy they are, they'll say, I'm 9 stone 6. And you look at them like, what? Yeah. Ask anybody in Europe, they'll give you an answer in kilograms. Ask them how tall they are, they'll give you an answer in meters. These are sensible answers. This strange value comes from this. It's called the autoionization of water. If you leave water alone, just leave it alone, it will undergo an equilibrium process, and it will split apart into its constituent ions. H+, the hydronium ion, which is acid, and hydroxide, which is base. Now it turns out that it does this very, very poorly. That concentration is 1 × 10⁻⁷ moles per liter. That means for every 10 million water molecules, only 1 of them splits apart. Okay? 1 out of every 10 million, because this is 10⁻⁷. That is the same as saying 0.00000001. 7 zeros, including the 1 before the decimal place. So 1 in 10 million water molecules splits apart like this. That 7 is the 7 that's right here. Because when this splits apart, 1 of these turns into 1 of those and 1 of these, which means that natural, pure water also must have 1 × 10⁻⁷ of the other ion as well. They have to be equal to each other. When they're equal to each other, the log of this number is -7. The negative log of it is 7. When these two values are the same, we are here. When this one starts to get larger than that one, we become basic. And when this one becomes larger than that one, we become acidic. Okay, so our values should be between 0 and 14. And we should probably, hey, we don't know anything at all about nature yet, but we should hope that it probably doesn't drift too far away from neutral. Okay.
So in the textbook,
Yeah.
one of the things it said was so the lowest ever recorded pH for acid rain occurred in 1974 in Scotland, and the pH was 2.4.
Not good.
That's it. Yeah, that's really acidic, right? I mean, like,
Mm-hmm.
so what happens? What happened with the people? Like, what did people get? Like acid burns?
No.
Okay.
No.
Okay, so that was the thing I was like trying to wrap my head around.
So this is kind of difficult because we teach two separate things that contradict each other at two separate times in a chemistry educational career. One is right up at the very beginning, all acids are the same. Doesn't matter which acid you've got. Acid plus base makes salt plus water. The net ionic equation of that is H plus OH minus equals H2O. The exact opposite of what I just wrote down. And that's always true, and you can always balance an acid-base neutralization no matter which acid, which base you use, because they're all the same. And then in lab this morning, we used 12 molar hydrochloric acid, and nobody's worried. We were wearing protective equipment, we were wearing glasses, and several students opted to wear gloves. But if I spilled that on my hands, I would just tidy up and I would casually walk to the sink and I'd wash my hands off. That has a pH that's actually lower than 0. It's off the scale. Okay. It's 12 molar. There's something else that we haven't told you. You can go below 0, but not there just yet. However, if I'd have spilled 12 molar sulfuric acid on my hands, I would immediately go to the sink. I would alert people to the hazard that I've left behind, and I would wash and wash and wash and wash and wash, and then I would wash some more. And then I would spend the rest of the day looking at my hand, waiting for something bad to happen before I wash it and or go to the emergency room. Because sulfuric acid is a dehydrating acid and hydrochloric acid isn't. Okay. So what acid got us down to a pH of 2?
It was not. It wasn't.
Yeah.
It was nitrate. No, it wasn't nitrate. Wait.
I didn't read the specific
I-
part.
I
But we
did,
can,
but
we can,
I didn't. You know what? I just
Yeah.
didn't read that part. It just didn't say. It was
So,
just
yeah,
talking about it in general, I think.
at 2, at a pH of 2, you know what that's like? That's like, oh, I just spilled lemon juice on me.
Okay.
Am I going to the hospital? No.
So yes, it's nitric oxide, and then.
So we're probably looking at nitrous acid and perhaps even sulfurous acid.
Sulfurous. It's sulfurous
Yeah.
acid. Yeah.
These will bump the needle,
Mm-hmm.
but they don't get down to the, not all, I've removed it now. Bases are much more injurious than acids are. If it's splashed with a base, I'm much more concerned than being splashed with an acid. And again, not all acids are the same. Nitric acid, leave a yellow stain, and if I don't get to it quick enough, it will stain me yellow. If I don't get to it quick enough, it will go brown and peel off. sulfuric acid will eat a hole into what I've got. Hydrochloric acid just bounces off. Okay, they're not all the same. So yeah. Okay. So here's where we live. Oh, look, there's a shed and a person and a tree and it's a sheep. It's one of those highly black-faced sheep.
Oh yeah.
They're very cute. And then here's a cloud. Oh, you know, I started asking this at the table the other day and never got to the final answer. When you look up in the sky and you see a big cumulus cloud, how much does that weigh? How much do clouds weigh?
Oh, well, I guess if it was only water, you could take the density of water. No, I don't know. No.
A cumulus cloud can be a cubic kilometer. It's a kilometer wide, a kilometer high, and a kilometer deep. About 4 tons.
I was like, that's very, very, very heavy.
About 4 tons. And little triggers, usually in pressure, will cause the particles of water that haven't really formed droplets yet to coalesce and dump. You can get 4 tons of water in your field. Yeah. All right, here's the water. It's raining down from the sky. And as it descends through this part of the atmosphere, if your gas is soluble in water, it's got this many minutes to dissolve in the descending water. Or up there while the cloud's still being formed, it could dissolve in that really tiny little droplets of water. What gases become acidic?
It'd be like the NOx or SOX. Oh, okay, I understand what you're asking now.
Non-metals. Only this part of the periodic table is non-metals. The rest of it are metals. If you take a metal and you burn it in oxygen, four sodiums, 2 oxygens. Sodium's a group 1 metal. And then I dissolve this in water. Oh, it's a base. You've made a base. The oxides of metals, when dissolved in water, become bases. The oxides of non-metals, when you dissolve them in water, become acids. It's one of those great times in science. We're always looking to compartmentalize. We're looking to subdivide and subcategorize. We've got a periodic table with 120 atoms on it. We want to know which ones are metals, which ones are non-metals. And now we know where all the acids come from. The acids come from the non-metals and the bases come from the metals. The metals do oxidation, the non-metals do reduction. I've got 2, not separate worlds, because they all inhabit the same world, but two separate behaviors in the same world. So the things that I'm concerned about are the oxides of non-metals. For many, many years, it was obvious what was at fault for acid rain.
The fireplaces, or, well, coal burning,
Yeah.
wood burning.
And coal is almost pure carbon.
Carbon, thank you. Oh my gosh.
For many, many years, it was absolutely obvious that burning carbon puts carbon dioxide into the atmosphere, and then that carbon dioxide returns back to Earth as carbonic acid. There's your acid rain. Guess what? It's not true. Carbon dioxide, coal does burn in oxygen to make carbon dioxide, which then does dissolve in water to make carbonic acid, which does return to the planet's surface as carbonic acid. But carbonic acid is not the source of acid rain, because I think we're looking for a pH. I wrote it down about 3.1. Acid rain has values
Says less than
lower than 4.4. With the category, if it's less than 3.5 of, oh, you are probably pulling more than your own weight, okay? Carbon dioxide can't go there for a bunch of reasons, which we're going to do we're going to prove something right now, because for the longest time it was obvious. We're burning coal, we're burning oil, we're burning carbon. Carbon makes carbon dioxide dissolves in water, makes carbonic acid. Carbonic acid is an acid, it has the word acid in its name, therefore this is the cause of acid rain. Only it's not. Because there's been carbon dioxide in the air for a long time. Its concentration is currently rising, but it's still a very, very small amount. Do we know what percentage of the Earth's atmosphere is carbon dioxide?
It's like less than 1%.
Oh, it's way less than 1%.
Wait, it's like
0.003%. And rising. It's about to turn into a 0.004. But it's still small, it's a small number, but it's, changing. And we probably don't want it to change. So we're going to go ahead and prove that this is not the culprit. Let's figure out why acid rain is what it is. Okay, so the rain because of man's pollution through industry, has become more acidic. Why should I care?
Because it can I mean, certain crops can't deal with that level of, I mean, between crops and then, I guess, into the, and going into our natural water systems and stuff.
Okay.
Problematic, I guess.
Okay.
Well, I mean, not, I guess.
When acid rain was first introduced to me as a student many years ago, it was presented this way. Those beautiful marble statues that the Romans made, marble and limestone are naturally basic rocks, as most mineral. Calcium oxide, calcium carbonate. Which side do they live on? They're from metals. They're the oxides of metals, or the complex oxides of metals. So they are basic. And then the acid rain is eroding them. So this was first presented to me long time ago of, this is a shame, you should do something about the acid rain, because our statues are losing their faces.
Oh, that's
That the
Taj
rain
Mahal too
is
or something.
eroding the features from art. Okay, well, what if you don't believe in sculpture? What if you don't believe that people should be iconic? What's the word? Yeah, Tom Brady just got a statue, right?
Yeah.
His is bronze. But what if they carved a marble statue of Tom Brady, and the rain in Boston, because it's acidic, made his features erode away? I couldn't care less. Couldn't care.
What kind of stone is the Mount Rushmore made out of?
Sandstone.
Chiseled out of the stone. It could well be limestone. It's probably limestone, because I don't think it was particularly hard to do.
So if it's limestone, it doesn't run. Oh, it's granite,
Oh,
which, it's greatly affected by acid rain, quartz and granite.
So it doesn't affect it?
Yeah, but it's
Doesn't.
mostly on the, it does affect it, but it's mostly on the East Coast, we don't have as much acidic rain in the Midwest. That's what people said anyways.
I'm including concrete in here.
Mm-hmm.
Concrete being a man-made stone. It's eroding our infrastructure. Now, I don't care if a statue loses its features over the course of 100 years. I do care if a bridge becomes unstable because the rain has eaten through the blocks that hold the bridge up. Okay, so this is an infrastructure one. It's not really a natural answer. Here's where, so it kills trees. It damages crops. And it does it not by, oh, raining on the leaves and now the leaves die. No, the leaves are sturdier than that. But it robs the nutrients from the soil. Because what do acids react with? Bases. And if you've got magnesium and calcium in your soil, then the acid reacts with them, solubilizes them, and then washes them away downstream to somewhere else. And as it washes downstream, because everything goes downstream, it changes the pH. In the ponds and the rivulets and other standing water. And it affects life that is sensitive to pH.
Like fishes?
Yeah, sure. So it's a knock-on effect. If the first thing that if the thing that's sensitive is, let's say snails, then, okay, so now I still have a pond full of fish, but I don't have snails. Well, the snails are cleaning the algae, and some of the fish eat the snails. And now they don't have food and they don't have algae to clean, and before you know it, oh, I've actually impacted this. So shells of shellfish, even at the really, really tiny level, are often calcium carbonate. They're biominerals. And if you put shellfish in acidic media, then their shells become thin and fail. And if you've got stuff that lives off them, then they lose a food source. Yeah, so it's always a knock-on effect of like, oh, I poured something that's antiseptic down the drain. Well, doesn't matter, it's antiseptic, it won't hurt anything. All it does is kill bugs. Well, it kills the bugs that the slightly bigger bugs live off, that then the fish live off, that then the birds live off. Right? It's part of the chain. So we just had a quick message of an obvious way where this is the biomineralization of shells. Anything, any mollusk or whatever, their shells are made, sometimes out of calcium carbonate.
Yep.
Yeah.
Yeah, and I know coral, there's a lot of corals specifically that are highly, highly sensitive to like, even the slightest like 0.1 of a pH change can just completely upturn them.
Yeah. All right.
Aquapora, that's the type. Those are super sensitive.
Yeah, all sorts of things. And it's a knock-on effect of you take something small out of the chain, well, it's going to have an impact somewhere else.
Then we use the bristle worms and the fish. Bristle worms.
Okay, let's go ahead and prove that carbon dioxide is not the cause of acid rain, because it can't get low enough. We are going to pull information from chemistry 2. Okay. Carbon dioxide cannot be the cause of acid rain because it doesn't dissolve well enough. Okay, so we've got two things to look at. We're going to write this forwards, and then we're going to write it backwards. And the backwards part isn't the same as the forwards one. I'm going to take carbon dioxide in the gas phase, and I'm going to react it with water. Oh, our book makes a very silly mistake at this point in its state symbol. Yeah, I don't know quite what it was thinking. Yeah.
I even wrote it down. I got mad at myself, so I just
This is carbonic acid. And carbonic acid is weak acid. Right? Acids are proton donors. They are the soluble ionic salts of the oxides of nonmetals. But it's only a weak acid, which means it doesn't dissociate 100%, not a strong electrolyte. So in order to be an acid, here you are, AQ means aqueous solution, L means liquid, G means gas. In order to be an acid, you have to give the H plus away. This is going to leave what's called, does our book call it bicarbonate or hydrogen carbonate?
I wrote it down as bicarbonate.
I'm fairly confident that our book's going to call this bicarbonate. All right. Correct name for this is hydrogen carbonate. All right, and this is the acid bit. There's my acid, giving it away. Now, if I write this as an arrow, it means that my reactant has turned into product and I've given away a lot of H+. In fact, all of the first set. Carbonic acid is what we call a diprotic acid. It has 2 hydrogens to give in 2 steps. The first step is always significantly easier than the second step because
well, kinetics, like rate law? Oh, because of yeah.
if I have to remove this H plus from that negatively charged thing, positives and negatives attract each other, whereas removing a positive from this is not as hard. But this is a weak acid, which means it doesn't dissociate fully, it doesn't ionize fully. It is subject to an equilibrium constant.
I wrote that one down. I don't remember equilibrium constants.
So, the equilibrium constant for anything is the concentration of the products divided by the concentration of the reactants. In this case, my product is H plus and HCO3 minus, and my reactant is H2CO3. This is the first acid ionization, and it has a value. This is K is a constant. It is 4.3 times 10 to the negative 7. And that's a value called Ka. In fact, it's Ka1 because it is the first of 2 possible hydrogens that this acid can give away. Ka1s are always the larger of the 2 values, sometimes by about 1,000. So the second one usually doesn't have very much influence over the acidity at all. It's usually all from the first one. And the fact that this is times 10 to the negative 7 tells us that the equilibrium, right, this number divided by this number is a very, very small number, which tells us the numbers on the top are themselves very, very small. Okay. The amount of carbon dioxide that is soluble in cold water is about 0.06 milligrams. How many milligrams are in a gram? 1,000. So this is, that would be a thousandth of a gram, and then down a position, and then down another position. This is 6 times 10 to the negative 5 grams. Not a lot. Not a lot. But then again, sometimes you don't need it to be a lot. Actually, I have a second decimal for it.
I was like, wait a second,
6.4.
oh wait. Okay, I got it. Sorry, I was doing that math in my head.
Let's go find the pH. Of rain that has fallen through a natural amount of carbon dioxide. So there's a point here that even if I put a whole bunch of carbon dioxide into the atmosphere, it doesn't dissolve very well in water. So only this amount of it's going to dissolve. Oh, and that is in 100 milliliters. Let's go ahead and find out what the pH of rain in the countryside is going to be. Okay, here's where we start. Moles of carbon dioxide is equal to mass carbon dioxide divided by formula mass of carbon dioxide. The mass is 6.4 times 10 to the negative 5 grams. Formula mass is the mass of carbon plus the mass of oxygen and then another oxygen, because the subscripted 2 multiplies only the atom that's immediately before it in the chemical formula. So this is a 12 and a 16 and a 16. If you're reading off the periodic table, it's 12.011 and 15.999. Our answer is going to be, oh, and this is in grams per mole. If you divide a number by itself and then by another number, the final answer comes out at the top, the bottom one. Okay? So this is 6.4 divided by 44.
That's bad. Okay. I have 1.45 times.
Yeah,
10.
so I'm only giving us 2 significant
1.5
figures.
times.
Oh,
10,
I thought it was
or
a
1.4.
four.
Okay.
Times 10 to the negative 6. That's how many volts we have. Okay. We're not doing this to very much precision. Okay, that's the number of moles. Now I need to know concentration. So concentration molarity is moles per liter. I'm doing this with solubility data. I'm turning it into concentration data. Solubility is mass per volume. Concentration is moles per liter. So the molarity of the dissolved carbon dioxide
is the moles of carbon dioxide divided by liters, which equals 1.4 times 10 to the negative 6 moles divided by 100 milliliters with a conversion factor that there are 1,000 milliliters in a liter. So this 100 milliliters is just 0.1. And 0.1 notches up that to 1.4 times 10 to the negative 5 moles per liter. Correct?
Yes.
Okay. Now, here's the deal. This represents carbon dioxide gas that's soluble in water as a liquid. But now, I'm talking about the concentration of carbon dioxide. There is no such thing, technically, well, you know, sort of. This dissolved carbon dioxide doesn't get to be dissolved carbon dioxide because it gets to be CO2 plus H2O makes H2CO3. So this is the concentration now of my carbonic acid. If I wanted to know what the concentration of argon dissolved in water was, argon has no chemical interaction with water, and I would have a concentration of a dissolved gas. But carbon dioxide undergoes a chemical change and becomes carbonic acid. Okay? All right. What I now need to do is find out how much of that carbonic acid has dissociated. So I'm going to find the concentration of H+. Okay. Here's how I'm going to do it. H2CO3 is in equilibrium with H+ and bicarbonate, and Ka is equal to, what was the value? 4.3?
Yes, times 10 to the
And
negative.
then okay. So that Ka represents the concentration of the H+ multiplied by the concentration of the hydrogen carbonates, all divided by the concentration of the carbonic acid. And it is equal to 4.3 times 10 to the negative 7. Okay. We're going to make an assumption. We're going to make an assumption that because this is a weak acid, it's still mostly intact. It's mostly undissociated. And we also have to assume that because this one thing, this guy, turns into these two at the same time, that the concentration of the acid is equal to the concentration of the hydrogen carbonate. Okay? All right. I'm going to make this be the variable that we're going to find. This should be familiar. I'm going to replace H with X. I'm going to multiply it by this value, X. I'm going to divide it by this value, which we found. And we're going to take a very, very small amount of it away and turn it into these two guys. So these two guys, my assumption is, because this is a very small number, my assumption is these two values are small, and they both came from this, okay? And because this is very, very small, x squared over 1.4 times 10 to the negative 5 is equal to 4.3 times 10 to the negative 7. Let's go ahead and rearrange this. X squared is 4, my accent slipped, 4.3 times 10 to the negative 7 multiplied by 1.4 times 10 to the negative 5. That's what x squared is, okay? So I'm not going to write the next line down because I'm on video. I don't have to leave everything on the board. X is the square root of everything under this hat. And X represents the concentration of H+. Go find that number.
This was chemistry 2, chaps on equilibrium, and we did them to death.
So if you saw what I did, I just did this. I multiplied them and then I rooted it. So 2.5 times 10 to the negative 6.
Yeah.
This tells us that the concentration of acid in naturally occurring rain that falls through carbon dioxide and absorbs all the carbon dioxide that it can is 2.5 micromolar. Okay? pH is negative log to the base 10 of the H+ concentration, which is the negative log of 2.5 times 10 to the negative 6, which equals,
That's right there. 5.6.
Already?
Yep.
5.60.
this is not
Oh yeah.
acidic enough to cause acid rain. The real culprits are the usual suspects at this point: sulfur oxides and nitrogen oxides. Sulfur dioxide combines with water to make sulfurous acid, and nitrogen monoxide combines with water to make nitrous acid. We need them to be nitric acid and sulfuric acid, not sulfurous and nitrous, before they are strong. Nitrous and sulfurous are stronger than carbonic, but not yet strong acids. So with what we've got, but we need to find whatever is the hidden pathway that turns sulfur dioxide into sulfur trioxide before we say, oh, I know what this is. Okay, and we'll do that on Thursday.